Thank you, everybody. Before forget, I want to acknowledge students and collaborators that helped me putting this presentation together. Ashvin on highway and Stefan on the way autopilot, Georg Schildbach on the parking sample, Stephanie and Teresa on human modeling, Jason and Sanyang on tire and vehicle models, Tony with Julia and LP, Youngjin and Melanie for autonomous drift, Alec for sensor fusion. The research that I'm presenting has been sponsored by Hyundai, Ford, NSF, and Office of Naval Research. This is an automated car. This is me driving towards Sacramento. It keeps the lane, as it keeps the safety distance from the front vehicle. If you want, it can also steer. Why you want to do that? Three main reasons. There are 40,000 people that die in the US every year. Europe has the same numbers. They say that if you put all the world together, it's like a Boeing falling from the sky every day. If you can coordinate autonomous car within smarter cities and traffic lights, you can reduce carbon emission. There's no doubt about that. And most importantly, people want to look at their phone instead of driving. So it's an old problem, right? In 1920, there was the first demo. You can look at Wikipedia. Europe had a lot of projects in the 80s with Mercedes-Benz. And if you follow this area, today you are overwhelmed by news about self-driving cars. You can read by yourself. I like this article from IEEE Explorer. Cars may think, but will they achieve artificial stupidity? FBI, the ones that can be used as lethal weapons. But the reality is that things are changing. If you see this is close to where I work. Apple is here, Google is here, this is Silicon Valley. In the past 5 years, all OEMs and tier one suppliers have basically moved or opened an office in the Silicon Valley. So that's a fact. 5 years ago, there was none of this. Also, what is true, today in California, you can get an autonomous driver's license. If you are an entity like for UC Berkeley or Hyundai, you can apply for this. It doesn't cost much, and you can let your vehicle drive on the road. Okay, so things are changing from a legislation, market, insurance point of view. I'm not going to talk about that. This talk is going to be about how do we engineer automated driving with focus on control. And I have 3 goals in the next 15 minutes or so. I want to give you an overview of our research activities, just an overview. I'll share with you a parking example that you can use in your advanced control class if you teach one. And I'll discuss just one result of our research is analog optimization. Hopefully, I'll be able to do all 3. So let's go back at the way we drive cars. This loop, human driving a vehicle that moves in an environment which is sensed by the human, works because humans uses forecast. And if you're not convinced, at the end of this presentation, you will be convinced. Even cars are designed so you can transmit forecasts, a blinking light, okay? So clearly, if you have a controller that uses a forecast on human, a forecast on vehicle dynamics, and forecast on environment, then the idea is that if that is well designed, you can make the whole driving experience safer. And if it's actually very well designed, then you can even remove the driver from the loop, and you have instead of an automated car, you have an autonomous car. So the idea why you want to use forecast is very simple, right? Because the vehicle has inertia, you have a region you want to avoid. This is dynamic because things around you are moving, and you really want to follow the green line rather than following the red line. Usually you have a state update model of your vehicle, which links the state at time k with the state at time k+1. And this function of some things you can control the vehicle and things you don't have control, the driver action and the environments around you. You want to keep your vehicle within your constraints based on the forecast of your uncertainty and the future steps. So how do you go from this very simple idea to actually designing in a systematic way control for autonomous drive? That's what I'm going to talk about next. There are really 3 main steps. Choose a good model abstraction, understand how good is your model by looking at your data, and third one, design your predictive control. So I'll describe the first 2 first, and then I'll talk about predictive control design next. Let's look. I want to share with you a little bit more about this loop. Okay, the human drives the vehicle using the classical interface. These are videos that we take in the lab to understand how this works. Many people think that it's obsolete, but actually works pretty well. Okay, steering, braking pads, braking pedals. Actually, when you change in modern cars, when you interact with the vehicle, you're really sending reference command to a lower level actuation system. So for instance, if you break your braking pad, if you push your braking pedal, you're really sending a command to an electronic control unit, which pushes 12 solenoids, which changes the pressure inside an hydraulic brake circuit, which moves your braking pads, which slow down your braking disc. And these are tests that we've been doing with the University of Torino, trying to understand the error between your reference versus the uncertain versus what you actually get in terms of pressure at the low-level control system. And today, in a modern car, this is a Hyundai Genesis 2015, you really have around 11 or 12 control actuation. You control braking torques, you control engine torque, you control front and rear distribution, you control steering, you control dampers for active suspension. This is not, this is everything on the standard model, series model. Now that you have controlled the vehicle moves in an environment. There are two interactions with your environment. The first one is with the ground. Okay? And the vehicle moves because you have tires. These are complicated objects. They are viscoelastic materials. There are conferences, the entire conference only on tires. These are, on the left-hand side, are finite element simulation that we use for studying this phenomena. What you see here is a tire patch, the contact between the tire and the ground from a top view. As you accelerate, the elements of the tire, they stretch. They go from red to orange, from green to orange to red, and when they're red, the element cannot stretch anymore, it's saturating. When the whole patch is red, the whole tire is slipping, okay? Complicated phenomena, control people use this curve. The classical longitudinal force is a function of the tire slip, which is the normalized difference between vehicle speed and wheel speed. If you accelerate, the more accelerate, the more longitudinal force you get, up to a point where actually your force decreases. That's when your tire starts slipping. Similar thing if you brake, okay? You brake, you push your braking pedals, you brake up to a point, and then you don't get, actually your braking force reduces. And the phenomenon is similar, depending, same shape, but different amplitude, whether you're on ice, snow, and asphalt. The other interaction is with the environment around you. So an autonomous car is equipped with LiDAR sensor. This is, you see, they're hidden here. There are 6. You have differential GPS, inertial measurement unit, cameras. This is an object recognized by the camera. You have radars. These are objects recognized by radars. And with all these sensors, you try to do simultaneous localization and mapping, classification of objects around you, full detection. This is the vehicle going around curve in Berkeley. You see all these objects. You see radar's object, LiDAR object with the cloud points. And there's a lot of interesting work in what is called sensor fusion. How do you put all these sensors together? You try to come up with a fused object with a reliable and robust estimation of the current scene and the forecasted scene. I'm not going to talk about that today. The focus on control. Once the car moves, in a regular car, there is a human that senses the environment that controls the vehicles. So this is the work really of neuroscientists, okay? And the way you sense the environment, you process and you actuate your limbs. It's very complicated. But there is, what's happened lately is that there is an agreement in the neuroscience community that we use a mental model, use a neural simulator in the brain to predict what happens in the future and base our action on that predictions. So if you use this paradigm of a mental model, then you explain why you need an ABS, anti-lock braking system, or a traction control. So your mental model is the green line. The real model is the red line. Okay, you think that the more you push, the more force you have, whether in traction or in braking. Instead, actually, in here, you need a traction control to accelerate. Here, you need an anti-lock braking system to decelerate. Okay, we do research in this area. For instance, if you look at longitudinal control, this is an expert driver doing a 90-degree curve. Okay, well, you see what he's doing is counter-steering. He's steering his wheels to the right, even if he wants to go to the left. This is because he's giving the vehicle a small side slip, which gives the maximum lateral force. Normal drivers actually don't have this mental model. Normal drivers are pretty bad. This is a 1-hour video collected after. It's the same situation. It's 90 degree. They don't go at high speed, but the road is slippery. So you are saturating the tires. Okay? And so we have been trying to understand what happens, why people do this type of crazy things. And usually I stop, there is a Fiat Cinquecento that goes around, and that's when I stop this 1-hour video, it comes now. Here is the theater just goes the other way around. Okay, so a lot of work in the past 10 years in my group on trying to understand human drivers. And the message is that there is lots of data that you can collect today. Data you have seen, data about the environment, data about the vehicle itself, also data about the driver itself. You can put cameras inside, and we have drivers that have high glass so that you can see in real time where they're looking at. If you have good models, then you can do better control. You can actually train less skilled humans, okay? And the challenge is really that if you look at the neuroscience world, it's a much more complicated affair. We are much more complicated problem. We are interested in personalized models rather than average mean behavior of a population. We are interested in a very complex task rather than moving a joystick in a controlled environment. And I don't trust simulators so much, so we really do experiments on the road, which are not where you have a lot of uncontrollable external factors. So what are these complex tasks that we ask the driver to do? They go from high drift to parking to driving on highway to driving an urban scene. Okay? And each of these scenarios has different challenges. So if you look at high, for instance, drifting here, there is no obstacle. We ask expert driver to bring the vehicle into a drift and then stop the vehicle at 180 degrees. And here what happens is actually a switch linear controller learned on the data works pretty well. It works so well that you can use the same controller to do the same maneuver autonomously. What the driver does, it destabilizes the vehicle, it controls the vehicle in the nonlinear region of the tire, and then it stabilizes back at this point to control to the linear region of the tire again. This is Youngjin and Melanie doing, the control is doing autonomous drift. This is a very fun project. I don't have time to talk about this. It would be plenary by itself. But you see here the smoke coming out. The driver is doing high drift condition. The robot is doing high drift condition at high speed, stabilizing the vehicle in the nonlinear regime. Parking. Very simple non-holonomic constraints. I'll share this example with you so you can teach in if you're interested in your control class. Georg Schildbach was here, and I've spent months on making this clean. This is something that humans are really bad at it. This is the control I'll share with. The same problem, okay, very simply and nicely solved with an online optimization, okay? We'll tell more about this, show you the models and the controller later. Spend a lot of work on highway driving. Something that works pretty well is using a hidden Markov model, where you model the joint distribution between traffic and driver's action. You can also use inside cameras information looking at the driver. As you collect data, you learn the modes as well as you transition between the modes. You see the different drivers here. You see the modes that are learned as you drive. At some point, it stops. And then when the model is learned, then you do an inference on the HMM to use this model to drive the vehicle. So why we need these models? For instance, lane keeping assist. This is a commercial feature today, and if you use the model, the project I showed you versus the commercial feature in terms of time, so this is time to lane crossing, you are able to predict lane departure half a second to 1 second early, and 1 second on a highway at 150 kilometers per hour, it's a lot, okay? Also, what you can do what is called personalized driving. I'll tell more about this. The idea is that the car drives the way you drive. And so these two charts show you that basically an average driver model is always worse than a personalized model regardless of the metric you use, whether it's a time to collision or a vehicle power, which is a metric on how aggressive you are. So here is our loop. I think the idea was to give you to explain a little bit more what's going on as you drive. And what is a good model abstraction? You usually have a classical Euler equation of motion, function of longitudinal position, speed, and yaw angle. You look at this product between lateral longitudinal speed and yaw rate. Forces to the wheels are described by nonlinear functions. You have cosinus that allows you to go from the local frame to the global frames. You have inequality constraint tell you the regions where you have to operate, and you have uncertain forecasts on the drivers, tires, and obstacles, okay? So, and clearly, this is the most complete model abstraction. Depending on which scenarios you're interested in, some of these will be more relevant than others. Okay, unless you are driving at high speed downtown when it's slippery and trying to park in a drift condition. So let's now that you've chosen your model abstraction, you want to do predictive control design. Okay, what do you do with this forecast? And the idea is that here is your requirement, here is your starting point to the left. You want a systematic way to design a controller, and this controller has to run in real time on your automotive embedded control platforms. This is the setup that I'm going to use to describe our research in this area. It's a classical finite time optimal control. You're looking for a set of feedback policy, pi 0, pi n minus 1, that minimize a cost function subject to nonlinear state update equation. And what you want to do, that the feedback policy you have to satisfy input and state constraints for all your support set of your uncertainty. What I'm going to talk about is about computation, okay, and computation, basically. How do you trade off conservatism versus complexity? So how do you compute this type of policy today? Very big picture, without going into much details, you have two options. One, I call it offline based, means that you pre-compute the feedback policy offline, and in real time, your evaluation of feedback policy at a given point is very simple, okay? So dynamic programming is one choice. It's only one of the possible choices. N greater than 5, number of states greater than 5 is basically impossible, okay? Because the simplest form that everybody uses, with the exception of a special class, is piecewise constant policy, which means you have to grid the state space. You cannot grid if you have n in this range. The other option is online based. Offline, what you do is just set up an optimization problem, and online uses a sophisticated algorithm that does a lot of computation. It gives you pi of x at a given point, okay? Nonlinear predictive control is one choice. There are hundreds of robotics algorithms here that fall in this class. Basic rule, avoid homemade solvers. I'll tell you more about this in a second. So I was looking, while I was doing this presentation, I looked back and say, well, what has changed in past 15 years? This is when I got my PhD, 15 years ago. And I said a very biased story here, but there are two things that have changed. One is that there are excellent non-convex open source solvers. They were not available 15 years ago, okay, regarding the online based. And if you look at the autonomous drive, few people really use it. Robotic algorithms like particle filter, rapid exploring random tree, and many, many others are prevailing, okay? And there's a very simple reason for this. General purpose optimization solvers do not allow for reusability, or what is called, operation research called this in-place problem modification. Very simple. If you solve a problem with an Horizon 5, you want to get and park in 5 steps, you cannot do it. You want to solve it in 6 steps, you have to repeat the optimization problem. You have to resolve everything again, all the linear algebra and everything. Robotics algorithms do this very well instead. Things are changing. If you use Julia, and if you use some optimization solvers, actually they do allow for in-place problem modification. Offline based, there is a new approach. You don't need to do dynamic programming, at least you don't need to grid. If your nonlinear system is a piecewise linear system, meaning that the state and input space is partitioned into regions, and in each region you have an affine model. The state, input, and uncertainty are polyhedral, and you have a piecewise linear and piecewise quadratic cost, either your expected cost or worst case cost. This goes back to my PhD. I like to show this slide. The feedback policy piecewise affine, and the regions in which you have these affine controllers have strange shape, depending linear or described as nonlinear inequalities, describing on which cost norm you use in the cost function. Short story is that there's really a new option. The feedback policy is piecewise affine if your system is polyhedral piecewise affine and has polyhedral constraints. What is the rule? It doesn't really matter the number of states because you're not gridding. Okay, you can solve problems in 100 dimensions with one constraint. Okay, so the number of constraints that become active over the horizon does not need to explore. And unfortunately, you don't know this unless you solve the problem. So you solve it if you can manage it, fine. Otherwise, you forget about this approach. It's been very powerful for small MPC problems, and there is a huge There's a number of very good people in this audience that have basically pushed the MPC, the real-time MPC effort in the past 10 years a lot. Very good online optimization algorithms, mixing option 1 with option 2, pre-compute more in offline. Lots of work on FPGA and GPU would be the list of people to acknowledge here would be too long. The fact is that if you look at the problem like this, if you're teaching advanced control class, this is a lateral stabilization of a vehicle. You have 4 states, longitudinal, you have 4 states, lateral speed, yaw rate, the error with respect to the yaw angle, desired yaw angle with the error with respect to the center lane. You want to stabilize this vehicle by acting on additional steering and braking. There is a driver that controls the speed and controls the steering, but it doesn't know how to drive. Okay, you have to help him. Well, you have nonlinear, you're doing this on ice. You have nonlinear tires. So you can piecewise linearize the tires. You have this piecewise linear model, 3 modes in the front, 3 modes in the rear. You have a 9-mode switch linear system. I don't trust this model, so I want a set value uncertainty. So you have a bound on each mode. So you have a piecewise linear system with uncertainty that enters additive and as well as multiplicative here, because the longitudinal speed is controlled by the driver. And you want to design a feedback controller that stabilizes this system. I do not know of any other way of doing this than the method I showed you before. You run this with MPT Toolbox, you get a few hundred regions, and you can upload it in the controller on the ECU. The driver thinks he's driving. Actually, the wheels are going in the other direction, and the controller is doing differential braking. That time, we didn't have the drone. Now we have cool videos with the drone looking at the wheels. Maybe I'll be able to show that. If you buy a Mercedes S, Class S, I know this is not the right audience. I cannot buy either. You basically have the controller project I showed you for doing adaptive cruise control is an explicit solution. Okay. If you're doing engine manipulation, this is a work they're doing with Honeywell, together with Jaroslav Pekar, who is in the audience, and Greg Stewart. There is this very cool tool that allows you to do control design for some classes of engines using this approach. Finishing parking example. This is one, and the reason why I'm showing this is where you cannot piecewise linearize. The things that I showed you that I did in my PhD thesis do not work. This is the simplest model is a kinematic bicycle model. You have a product between cosinus and velocity. It is a 4-state system. You control acceleration A and of the vehicle and the steering angle delta. Okay. No way you can piecewise linearize this. Okay, so how do I design control design? Let's make it even simpler. Let's assume I go at constant speed, okay, at constant steering angle for some pieces of my travel. So your unknown becomes the distance between the rear axis and the instantaneous center of rotation, r. So this goes to infinity when you're going, r goes to infinity when you're going straight. And beta, the traveled angle along your arc. You go from a kinematic model to a geometric model. Here is a very simple equation. If you use a distance r and you travel beta, the next time step you'll be in this, the equation next time step I'll describe by these 3 simple equations, okay? Very super simple geometric model. You wanna design a controller that parks in a given spot. You have vertical parking, tilted parking, parallel parking. You have nonlinear, you have a disconnected set of your R, right? Because you can turn left, right, so you go from minus infinity to a minimum radius, and from plus infinity to a minimum radius. Then you are given obstacles. You have initial position, x, y, and your angle, terminal x, y, and your angle. Okay, so you can park, it's a 3-dimensional problem, and you want to find the input sequence which parks the vehicle. So Georg and I, this is what we want to share with you. You go on mpc.berkeley software. There is the software for solving this problem with dynamic programming and with online optimization. Okay? I spent Georg and I spent literally 2 months to cleaning this up, and I'll be using this in my advanced control class because I was fed up of teaching dynamic programming for linear x dot equal x plus pu. So by the way, what are the results here? if you're doing online optimization, or if you're computing the feedback policy, it takes the same time. It takes, milliseconds for 2 steps, 2 segments, half an hour for if you're using multiple steps. But this one is for a given point. This one is the whole policy. So dynamic programming for this in 3 dimensions, really it's 1,000 times faster. That's really what you want to do. What are the challenges? You really have, for nonlinear programming, you really have 1 parameter, the horizon length. Dynamic programming, 500 lines of code and 25 parameters, because you have to grid in 3 dimensions, you have to grid the input space. Complicated piece of software that Georg has done a very good job with. You have seen this, the car bouncing. This is a geometry. You're just computing the path. So you need still to compute the acceleration to your vehicle. So you're going to have a low-level path following problem. Instead, if you're using a kinematic model, you're computing steering and acceleration at the same time. Dynamic programming using kinematic models, so you go in 5 dimension, not a classroom example. Okay. If you have a different obstacle configuration, you have to recompute dynamic programming again. Right? You have to recompute the whole policy. Nonlinear optimization is actually you just change the setup in real time. So here is, actually the other thing that I like about the nonlinear optimization. That's the code. Here it is. It's not a pseudocode. This is the Julia code for doing parking. You can actually go download it. Here is the 3 constraints. By the way, you can use R and beta and psi in your code. This is the model. You have system constraints that I showed before. You want to do obstacle avoidance. You take a vertex here. You have to do this for all vertices of the car. You take a vertex and you say the vertex has to be either on this side or on this side of this obstacle. And you code this with the classical disjunction. Okay, it's not the best way of doing it, but it's very clean. Lambda times the constraint plus lambda 2 times the other constraint is greater than 0. The sum of the 2 lambda is 1. For lambda positive, this is an OR. Okay? This is the code. You download it. You download Julia. It takes 1 hour to learn Julia. You run it and actually makes also the video at the end. Okay? Again, this was an example that I want to share because at the end of my plannings, I always say, this is interesting, but what do I do with it? So this is something that you can use in your class if you're interested in. So what if, let's move to the second part. What happens if you can't compute this policy? Okay? Lots of interesting things that you can do. This is the area of model predictive control. There are references in the papers. Many smart people work in this area. But a few very big picture is the following. The first thing you can do is shorten your horizon. Okay, and the horizon is too short, it's too long, make it shorter. What you need to do, you need to add a terminal set to make sure that where you land satisfy the state where you land will, from the state where you land, you'll be able to satisfy the constraints. We do use this approach. For instance, in our highway pilot, we let the driver model drive, and then we have a safety set, which is called a robust invariant set at the end. This is a scenario. There was a car that cut in. The autopilot didn't decelerate enough, and so the lower level control system, to enforce the robust constraint, added an additional braking force. Parking. This is a very tight spot. Okay? If you try to solve from this problem with dynamic programming or linear optimization, you won't be able to do it. It takes hours to solve. So the way you solve this, you pre-compute this object. It's a reachable set. From here to here, you have pre-computed solutions. And then in real time, you just try to get to this point. Okay? So this is a video that shows this parking maneuver. And you see from here now, once you're in the set, the pre-computed policy works. And by the way, you see these movements going back and forth, back and forth. There's no way you can find that with an online optimization or with dynamic programming. It would require a fine grid. Okay? So the other thing you can do is to change, instead of looking for any feedback policy, you look for just a subset of feedback policy. You can look for just linear feedback policy over the horizon or just constant policy over the horizon, because you are re-optimizing anyway. As you go down in this list, the set of feasible states shrinks, meaning that the car will be safe, will travel only at very low speed on highway. The parking problem you'll be able to solve parking only for a given set of configuration. because the set shrinks, then the other, what you can do, you can, instead of doing robust constraint satisfaction, you can relax the constraint satisfaction, allow for the constraint being violated only of a small epsilon. You heard beautiful plenary this morning about this topic. Big picture is that it's a challenging problem, right? You have to, now the uncertainty is a random variable, you have to propagate the statistics, and you have to transform the chance constraint into the deterministic constraint, and this is a multivariate integral, complicated to solve. Two main big area, explicit method and particle method, sample-based methods here. We are using both, and you can, I can talk more about this later. Last thing, last option that you have, once you have transformed the optimization problem into a mathematical program where the initial state changes the right-hand side of the equality and equality constraint, the cost function, this problem is a special structure. This is block diagonal. You can exploit the structure and run this fast on embedded hardware. There are interesting, it is an interesting European project trying to focus on this. The idea was to give you an overview of the research we do. We do research in this area, okay? And we do use all these things to make a nice design, systematic design of our autonomous highway car. We have a driver model that drives the vehicles, a personalized driving. You can drive the way Ashwin or Stephanie drives. You forecast the scene. And by the way, if you want to know more details for forecasting the scene, we use a Markov jump linear system. The way people drive around you are estimated in real time using least square and clustering, okay, so that you can quickly understand what they are doing. Once you have forecasted the scene, we use an invariant set, the terminal set, to enforce the safety. To make it destructible, you have linear time varying model plus affine feedback policies. And we use chance constraints. This part here is quite standard. You can look at the MPC literature. You usually linearize around previous trajectories. You optimize around feedback policy. If you assume these are Gaussian disturbances, then that the disturbance is Gaussian, then you have explicit formulas to propagate the statistics. And this is an example that shows basically when there is a car, this is the actual trajectory, and this is our forecasted trajectory. It becomes bimodal really for a few seconds, where you really don't know if it's going to turn left or right. Otherwise, a Gaussian approximation is not too bad. Georg Schildbach is exploiting recently more scenario generation for this class of problems, and it's interesting because in this board there are interaction-aware models. So, and doing statistical computation with joint probability distribution is very complicated. This seems to be a more natural way of doing it, where you sample the possible trajectory, you reject things that are not likely to happen because this will lead to a collision. You can talk to Georg for more details about this. This is the experiment that I showed you before. I'll joke with my students, before you need one person to drive, now you need the person looking at the students next to that's looking at the computer. You need two people to drive an autonomous car. Here you see changing the driving style. So I'm switching to Stephanie mode. Stephanie likes to drive close to the cars. The time where I was almost taking action here is because actually the LiDAR didn't see this obstacle to the left. It was quite dangerous. I don't play this long time because, you know, when people show you videos, they're always the time when it works. You don't know all the times it doesn't work. Actually, it's more interesting when it doesn't work. This is me not playing with the phone. Here, there was a cut-in vehicle. The safety set kicks in. The controller breaks more than the driver model, and things goes on. Well, this concludes the first part of my talk. In the last, I believe, 10, 15 minutes, I want to show you the details of one research result. As I say, we do research in these areas, and recently, 3 or 4 years ago, we started looking at how to solve these optimization problems that derive from optimal control problems really fast. Okay, lots of work in this area, and what we did was to plot, at that time, some solvers, published solvers in the literature, MPC solvers. Size of the problem, meaning the number of variables and number of constraints, versus the time it takes to solve a problem for each given state. If your solver is not in here, don't worry. This is an old thing, and there are many solvers on the right-hand side here. The message here was not really to compare different solvers. The idea was trying to show you that we looked at this chart and say, we want to understand, we want to do research that allows a solver to solve in this area, meaning tens of hundreds of variables in nanoseconds. And the only way you can do that is to go and move to analog optimization. This was, Sergey started working on it. I was very skeptical 4 or 5 years ago, and now I'm presenting it because I think it's actually a pretty cool result. The other reason is, if you look at CPU speed, basically has been stalled for the past 10 years. This is the clock speed from the 70 until now, and there's really no progress on single task improvement, right? So putting the two plots together, we said, well, let's try to go back to analog optimization and see if we can do anything interesting. Final result is we designed a very simple electrical network that solves quadratic programming problem with changing right-hand side. So this is a QP, a convex with strictly positive definite Q. So it's a convex QP. You change the right-hand side here, and you want to solve this problem. You want to change the right-hand side because you want to solve this problem as new initial state becomes available, as your scene around you changes, okay, in your driving vehicles. The elements, this circuit is super simple. And that's also why I've decided, I think in 10 minutes I can explain you the main idea. The dots here are resistors connected in this way. So the resistors are computed from the equality constraints of the QP, the inequality constraints, and the cost matrix. So, or a set of resistors that are linked to the cost matrix. The right-hand side is changed through voltage sources here. And the resistors, the circuit has only positive resistors, they're all the dots. Negative resistors, I'll say more about this, they are here. Voltage source and diodes for inequality constraint. How does it work? Very simple idea. You use basic Kirchhoff laws. If you take a set of n resistors connected to a common node, U, you know that the voltage in U is proportional to the voltage drop across the resistor using this formula here. If you set the voltage U to this equation here, then you end up with a set of equality constraints on V1, Vk, Vn of these voltages. So what you have to enforce, U, these voltages, to be equal to this right-hand side. This right-hand side is, this quantity is a positive, it's B changes, right? So this is a voltage source. And then the sum minus I is a negative resistor. So if you take this mesh of resistors, you put a negative resistor here. This negative resistor is a function of these resistors here. And you have a voltage source. You have an equality constraint. Then you can change the right-hand side of the equality constraint by just changing the voltage source. If you take now, put a diode in, then you have an inequality constraint. Okay? If now you have equality constraint, you have inequality constraint, now you want to minimize your quadratic cost. Just use fundamental laws. You know that for a given input current, the distribution of currents will be such that the least power dissipation will be achieved, which means that if you have n resistors, you're minimizing connected here, the current will distribute so that you minimize this Q function of the n resistors. Short story, put all together, you create linear equality constraints and linear inequality constraints just from your A matrix. You need resistors, negative resistors, and voltage source. Then you are given a Q, and you add these additional rows of resistors so that the total dissipation is equal to your Q. And there are formulas in the paper how to compute A1 and AS. You combine all together, and you have a circuit that solves your QP. And the way you prove it, the KKT conditions, you write down the KKT condition of the QP, you write down the electrical equation of the circuit, and they are the same. it turns out, not surprisingly, that the currents represent the dual variables and the diode enforce complementary slackness condition. Does it work? Okay, so this is the first question I always ask. Now, the circuit is pretty simple. You see, this is why it's fast, because there is no, and this is the main difference with the work in the 80s. The work in the 80s had capacitors and complicated things everywhere. This is a resistor mesh, equality constraints, inequality constraint, cost function. The problem is really these switches and the negative resistance. So you really have to see how do you code that. The negative resistance, you can implement it using an operation amplifier. The switches have a major parasitic effect, so they have this capacitance here. And then you take the positive resistance, you model them just as an equivalent network. So you have negative resistance as an operation amplifier. The switch is a diode model with a parasitic capacitance C. The network, it just, you lump this all together with Rm. And this circuit now can be unstable because it's an electric circuit with switches and negative resistance. Clearly can be unstable. So I've been trying to understand how can I make this circuit stable. And the model, what you do, you model the whole network as a fine hybrid system. Here is your positive resistor network. Here is the negative resistors and the switches here for the inequality constraints. You put all together, you end up with a fine switch system. The switches are a function of the diode state. The A matrix of your affine system is a function of the coupling, depending on which switch is open and which is closed. And there's a block diagonal term here on each row here, represented by the equality, inequality, and cost circuit. And this element is a 2x2 matrix, which is function of epsilon and gamma. Epsilon is the inverse of the operation amplifier gain. You scale the QP so that you have all the same operation amplifier everywhere. You can do that. And the gamma is the ratio between the RC time constant of this circuit and the time constant of the operation amplifier. Okay? So what we can do, we've been looking for quite some time for a piecewise quadratic Lyapunov function, almost for 6 months. Sergey was able to do it with some help. And a piecewise quadratic, the final result is the following. That I'll explain this result a little bit in details, that for any epsilon, there is a gamma critical for which the circuit is globally asymptotically stable. So what does it mean? And actually, the proof is constructive. It tells you you can actually compute the gamma critical, okay, and requires eigenvalue decomposition and the KYP lemma. I thought that it's after lunch, people are sleeping by now. There's no, you probably don't want to see the proof. How do you use this proof? How do you use this theorem? So the first thing you do, you set the operation amplifier gain, okay, based on the technology you want to use. So you have an epsilon. For a given epsilon, you go in this chart and you look at your gamma critical. Okay, that sets an upper bound to your gamma. Gamma is this element here. R and C are given by your QP problem and your technology. K is the operation amplifier gain, and tau is the time constant of the operation amplifier gain. So basically, setting an upper bound, it means you have an upper bound on the speed of the operation amplifier. So you find the gamma critical sets an upper bound of the gain bandwidth product of the operation amplifier. Okay? So here, if you take a VLSI technology, you use 1 kilo-ohm, the numbers in here, 10 femtofarads of capacitance, you get a gain bandwidth product of 100 gigahertz, which means that you can get convergence in the order of nanoseconds. And this was very interesting. Okay? This is why I thought I could show this result. Summarizing, it's an old, analog optimization is an old, has been explored in the past. Then it died because of digital area, and I thought I wouldn't be presenting this today, but I'm quite excited about this. The circuit was too complex and it would take forever to converge. The circuit is so simple that we actually print in them, the one I've designed. You have a proof of convergence, and the PCB board, actually I decided, does it really work? So this is when we decided, okay, let's print the circuit. This is a PCB board. We've printed 5 or 10 of this. I wanted to bring it, but I thought that security would stop me, so I've printed. And this solves a QP problem with 21 variables, 6 equality constraints, 8 inequality constraints, and 10 equality constraints of this type. This is faster than any of your laptops solving this problem. It has only 40 operation amplifier and 100 resistors. It's actually, the resistors are, they're potentiometers. You can change it, you can solve any QP you want. The reason why we chose this number is because we wanted to solve the fastest QP you have seen in that chart, which was for a buck DC-DC converter. Okay? It also does linear computation. It does linear algebra much faster than your computer. You can actually have, this board does also the linear observer together with the QP optimization. Here is the results. You have accuracy, which is a big problem always, but better than 1%. You have 80 microseconds to solve the problem for all different initial conditions. If you take your fastest laptop, Gurobi will take 3 milliseconds. CVX will take 300 milliseconds. Okay, this is the fastest computer in this room. There are issues, and I'll be happy to discuss about this. And because people in my group, they're crazy about videos because of the autonomous drive, here is a video of the circuit. What's happening here is that you have the 21 variables. You are comparing digital versus quad prog. Clearly, they're one on top of each other. You have 1% accuracy. You change the right-hand side. You see these things moving, some constraint becoming active. Okay, and then you change, and the other different constraints are not active. You can close the loop. This is the circuit controlling a model of the DC-DC converter. It works, clearly. And then we went further, and we have designed a VLSI prototype. We haven't printed this yet. This was a whole master thesis by Crystal. Crystal and advisor Elad decided to move away from resistors network. Problems I can explain to you later, but we went to switch differential capacitor circuits. So the variables are coded as capacitors here, okay? So this is a very small QP. It's a QP, I think, 5 by 5, and it's high-fidelity simulation. This is the last simulation before printing the VLSI circuit. This is the time constants are 50 nanoseconds, accuracy better than 1%. Power of 200 picojoule to solve the QP. Your computer actually takes 500 picojoule per flop. This is 200 picojoules to solve the QP. Your computer is 500 picojoule per flop. Okay, better hardwares will go from 50. The range is from 50 to 500. I think on this note, this is all what I wanted to do. I am done with my talk. I want to give you an overview of how to engineer automated driving, tell a little bit more what we are doing at Berkeley with our research activities, share with you a parking example. If you're fed up of your x dot equal x plus bu, you can use the code and the example, which is quite neat for parking the car. And then I want to discuss just one result, which was an analog optimization. It's an interesting problem. There's lots of control problems in there, real-time optimization, filtering, fault detection. For some reason, it's dominated by the robotic community, and I don't know why. And there's also very interesting questions on what happens if the car kills a pedestrian that they're interesting, but I didn't have time to talk about. My personal view here is that there will be more need of real-time optimization with data feeds. And there will be a lot of work on embedding humans rather than disconnecting humans. If everybody tells you there are 40,000 people that die every year in the United States or in Europe, nobody tells you how good we are. We have one death every 100 million vehicle miles. And this is in every condition. This is slippery, drunk driving, everything. Okay? So that's actually the goal that you have to achieve with an autonomous car. If you're applying for an autonomous driver license, all the rules are about the human. You can read this, but it's written here, driver, autonomous operator. They don't call it a driver, they call it the operator. So it's all about how do you interface with the operator, okay? And when people ask me how long it's gonna take, well, it took 40 years for a very simple system, which is ABS, anti-lock braking system. That's 4 sensors, 1 actuator. From the 70s when it was introduced, when in the US has become mandatory since 2011. So hopefully this time will go faster. Thank you.
I think we have perhaps time for a couple of questions from the audience. Any questions?
Yep. No, I was curious when you talked about negative resistance. Could you speak a bit about the negative resistance you talked about?
Yes. Yes. So what are the challenges with the negative resistance? There are two challenges. One is stability. And this thing addresses these challenges. If you slow down the operational amplifier, you have no problems. Okay? The intuition is that you have a negative resistance here. You have a capacitor and a positive resistance. You basically want to discharge to the positive faster than what you're charging through the negative resistance. That's the basic intuition. So you have to slow down the negative resistance. You can do that. The challenge actually is not, well, which means that the circle becomes slower. But you can do it in nanoseconds that I show you. The biggest challenge is actually the negative resistance is, you see here, is minus these sums, and these sums are the input of your QP. So it has to be exactly the sum of this, or 1 divided the sum. And this matching is the more complicated part. Because especially when you use digital potentiometer in the board, you have nonlinear effect. They don't match exactly. If you don't match exactly, you're not solving the QP problem. And that's why in the VLSI, we went to this switch capacitor thing. This is a problem that the VLSI community knows very well, luckily. Okay.
Okay, other questions? All right. Okay, there is a question over there.
Oh. What is coming? Assisted systems are out there. Okay. We didn't have enough time, but actually this is the biggest problem today, that people are misusing the assisted system. There is a video on YouTube, I'll share the link with you, of somebody in Europe sitting on Q infinity. And the Q infinity has a lane keeping system. It means that you turn it on, it keeps the lane, and it keeps a given distance from the front vehicle. Okay? The guy goes in the back seat and records his vehicle. Okay? And so they are out there. You can buy it, you can misuse them. Okay? In the US, in order to avoid that, you have a minimum time that you can remove your hands from the wheels. Okay? And you can sense that with the steering torque sensor there. So, which is not active in Europe. So assisted systems are out there. How to move that toward autonomous is the biggest challenge, and it's an insurance, it's a market issue. It's a very interesting problem.
Okay, one more question here.
First, thank you very much for a very impressive talk.
Welcome.
It seems the Markov process, Markov design process is still part of the story, right? So that when I think about this car is a very big inertia for small sampling interval. If you sample faster, it's actually pretty much a deterministic system between samples. So I fail to understand why that was a Markov, the including noise is important.
So it's a very good point. First of all, the whole approach doesn't depend on the way you generate forecasts. So you can generate forecasts with uncertainty, or you can generate nominal forecasts if you like. Why do we use? When do you need uncertainty? That's a very good point. The biggest challenge is really depends what type of problem are you solving. Okay, for planning problems, where you need to know where the other vehicles are going, that's where you need some type of Markov process. Okay, this is where it's bimodal. Maybe the vehicle is steering, and this is multiple seconds ahead, 5 to 10 seconds. For the next millisecond or 50 milliseconds, you don't need any of that.
Okay, so maybe it's the time for us to thank our speaker for a really excellent talk.